Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to be talking about Chapter 9 of the IB Chem SL curriculum, talking about redox processes. Now, scientists have observed oxidation-reduction reactions for many years, and early attempts to define these were centered around either the gain or loss of oxygen, or the gain or loss of hydrogen. But a more modern understanding of oxidation reduction is in terms of electrons. So when you're losing electrons, it's oxidation, and when you're gaining electrons, it's reduction. So there might be two ways that you have heard to remember this. Either Leo goes Ger, the lion goes Ger. Leo for loss of electrons, Ger for gain of electrons. Or OILRIG, oxidation is the loss of electrons, reduction is gain of electrons. Let's take a look at an equation. So we have here magnesium burning with oxygen to form magnesium oxide. This is actually an oxidation reduction reaction. One of the species is gaining electrons and the other one is losing electrons. So let's take a look. We see here that magnesium is actually forming the magnesium 2+ ion. And so it's actually it's actually losing electrons, becoming more positive. And so losing electrons, Leo goes Ger, so loss of electrons is oxidation, while the oxygen is gaining electrons. And so when you're gaining electrons, that's reduction. Let's take a look at another example. Here's magnesium reacting with nitrogen in the air. And again, this is an oxidation reduction reaction. Magnesium is losing electrons, it's becoming more positive, and nitrogen is gaining electrons, it's becoming more negative. And so we have to assign oxidation states to figure out if atoms are losing or gaining electrons. And here are a couple rules to follow. If there is no charge, then the oxidation state of the atom is 0. If there is a charge, then the oxidation state of that atom is going to be equal to the charge. If you have a bunch of atoms compounded together and there is no charge, then the sum of all of those atoms, the oxidation state is 0. If there is a charge, however, the sum of the oxidation states equals the charge. So usually the oxidation state is the same as the charge, and we'll take a look at that in the next chart. Okay. So these are group 1 elements. Lithium, sodium, and potassium. So group 1 have a charge of +1, so the usual oxidation state is +1. Magnesium and calcium is group 2, so usually +2. Fluorine is usually -1. Oxygen is usually -2. There are some exceptions here. Hydrogen is usually +1, and chlorine is usually -1. Using these as the base rules, we can figure out everything else pretty much by using these as the base rules that we just went over. So let's take a look at some examples. H2S, so we want to figure out the oxidation state of sulfur. Since each hydrogen is +1 and the overall oxidation state is 0, the two hydrogens will give us a +2, so sulfur should be -2. Sulfur by itself without a charge is going to have an oxidation state of 0. Chlorines are -1, and since we have 2 of them and the overall charge is 0, sulfur has to be +2. In this case, this oxygen is -2, and there are 2 of them, so that's -4 with an overall charge of 0. So sulfur has to be +4. In this case, the oxygens give us a -6, -2 for each, but we notice the overall charge is 2-. So the sulfur here also is +4. In the sulfate ion, SO3, you see there's no overall charge, and so sulfur has to be +6 to cancel out the -2 of each of these oxygens. What about this one, H2SO4? Well, these oxygens give us a total of -8, and these two hydrogens will give us +2, so -8 and +2 will give us a total of +6. Now, to name some of the other ones, we have to use the Roman numerals to identify the oxidation state or the charge of those elements. And so FeO, we know that O is -2, so Fe has to be +2. But there are cases where, so we write in iron 2 oxide. But there are cases where the iron is +3, so we write iron 3 oxide. Same thing with copper. Here, oxygen is -2, so each copper should be +1. And we can see that notated by the Roman numerals with each element. So let's deduce the name of the following compounds using oxidation numbers. V2O5, vanadium oxide. So oxygen is going to give us -2, 5 of them is -10, so each vanadium has to be +5. NiOH2, so the OH, this is -2 and this is +1, so the OH together is a -1, and there are 2 of them, so that's -2, so Ni has to be +2. Each Cl is -1, so titanium has to be +4. Now let's name these. The charge is 5, so it's vanadium oxide with a Roman numeral 5. Nickel is +2, and so we're going to put a 2 nickel hydroxide. Titanium is 4, and so we're going to put 4 titanium chloride.